Okay, here we're going to be talking about exact DEs. So we have some differential equation in differential form. Remember, that's some function we called m dx plus some other function n dy equals 0. A DE is exact if the partial of m with respect to y is the same thing as the partial of n with respect to x. The only way that could happen is if this entire DE was actually the full complete differential of some higher order function f, which means the m is actually somebody's partial with respect to x, and n is somebody's partial with respect to y. Okay, so there's a lot going on here. Be careful with this. This guy is somebody's partial with respect to x. He's beside dx. This guy is somebody's partial with respect to y, and he's beside dy. Remember, from differential or from Calc 3, if a function is continuous, the mixed partials are equal. Remember that the second partial for any continuous function, the second partial of f with respect to y and x, so you do it with x first, then y, that's the same thing as if you do it with respect to y first and then with respect to x. The mixed partials are equivalent. So if these guys are equal, that means the mixed partials of some higher order function f are equal, so f must be continuous. So we've got this function f. Remember, the differential of a function, df, is partial f respect to x dx plus partial f respect to y dy. That's the full differential. So if these two things are the same, this guy m must be this piece here, partial with respect to x, and this guy must have been his partial with respect to y. But we're told that that whole thing equals 0. So we have a full differential equal to 0. The only way that the differential could equal 0 is if the function is equal to a constant to begin with. So once we find this function f, we set him equal to a constant and we're done. But we know stuff about f. He is or m up here is his partial with respect to x. So if I integrate m, I should get back to f. But the problem is, if there were some extra y's floating around, they may have gotten lost when I took partial with respect to x. So I might have an additional function of y whose derivative with respect to x was 0. But f is also the antiderivative of n with respect to y, plus maybe some arbitrary function of x. Okay, none of this will make sense until we look at a couple of examples. Okay, so we'll start with a really simple example. So I've got this DE, 2x minus 1 dx plus 3y plus 7 dy equals 0. This is an exact DE. M, the stuff in front of dx, is 2x minus 1. N, the stuff in front of dy, is 3y plus 7. I check the mixed partials. So I take partial of m with respect to y. He was sitting beside dx. I take his partial with respect to y. I get 0. There are no y's there. N was sitting next to y, dy. I take his partial with respect to x. There are no x's in there, so his partial with respect to x is 0. We got the same thing. Those are the same. So this DE is what we call an exact DE. That means this DE is the full differential of this guy f we're after. Okay, so to find f, I take the integral of m dx. So notice here, I took partial with respect to y. I integrate with respect to x, the guy that he was sitting next to. Okay, so the antiderivative of 2x minus 1 would be x squared minus x. Now, if I took the derivative of that, I would get this back. But what if there had been an extra y squared hanging out? When I took the derivative with respect to x, that would have disappeared. So there may be some extra y's. We call it just an arbitrary function of y. There may be some extra y's hanging out in f that we didn't get yet. So one approach now is to take this guy's derivative with respect to y and see what was missing up here in n, but I don't like that way. I prefer repeat this process. Integrate n with respect to y. He was sitting next to y. We integrate him with respect to y. So the antiderivative of 3y plus 7 would be 3y squared over 2 plus 7y, plus possibly an arbitrary function of x. And now we mix and match our pieces. So anything you see, you know you're going to need in f. Write down everything you see. If something appears in both versions, just write it once. And that's really all you're doing. You're just copying down everything you see. So that extra function of y that was missing, oh, it was all this stuff right here. That extra function of x that was missing, oh, it was all that stuff I got up here. If I have anything in both versions, I just write it down once, and then I write down everything I see in either, so I just write all of it down. So that's my function f. Now the whole key to exact DEs is this, what we wrote here, is the differential of x. You should check that on your own. Take the differential. Remember, the differential is partial with respect to x dx plus partial with respect to y dy. So pause the video, write down this function, take his differential. You should have gotten this. That right there is m. That right there is n. But we're told that equals 0. Like that's our original DE. That differential must equal 0. The only way that the full differential of a function can equal 0 is if that function himself equals a constant. So here's our solution.